the phasor analysis of RC series circuit. We consider the RC series circuit in figure number 3.50, and we are going to find out the phasor value of the AC current in this series combination, the phasor value of the AC voltage across the resistor, the phasor value of the voltage across the capacitor, and the phasor value of the voltage across the source. We can represent the AC current with the help of a phasor quantity if the RMS value of this current and the phase angle of this current are known. Similarly, if the RMS value of the voltage across the resistor and its phase angle are known, we can find out the phasor value of this AC voltage. We can find out the phasor value of the AC voltage across the capacitor if the RMS value of this voltage and the phase angle of this voltage are known. Similarly, we can find out the phasor value of the applied voltage if the RMS value of this voltage is known and the phase angle of this voltage is known. So we consider the instantaneous equation for the AC current in this series combination. And omega t in this equation can be written as, we have omega t plus 0. So the phase angle of this voltage, omega t can be written as omega t plus 0. The phase angle of this AC current is 0. So we consider this current as a reference current. This is a reference current. This is why the phase angle of this current is 0. We shall consider the phase angle of the voltage across the resistor with respect to this current. We shall consider the phase angle of the AC voltage across the capacitor with respect to this current. And we shall consider the phase angle of the source voltage with respect to this current. So the current in this series combination is a reference quantity. The phase angles of all the other electrical quantities in this series combination will be considered with respect to current. So anyhow, the phase angle of this AC current is 0. Let us calculate the RMS value of this AC current. In order to calculate the RMS value of this AC current, we divide its maximum value by under root 2. So the division of the maximum value of this AC current by under root 2 results in the RMS value of this AC current. As the RMS value of this current has been calculated and the phase angle of this AC current is known, we can represent this AC current with the help of a phasor quantity. So this is the AC current, this is the phasor value of this AC current, and this AC current is in polar form. The magnitude of this phasor is equal to the RMS value of this AC current, and the angle of this phasor is equal to the phase angle of this AC current. So the AC current is in polar form. We convert the polar form of representation into rectangular form. If we convert this polar form into rectangular form, the imaginary component of this AC current will be 0, and this current will have the real component only. So the real component of this AC current will be equal to the RMS value of this AC current, and the imaginary component of the AC current will be 0. So current is a real quantity. Current is a real phasor. As it is a real phasor, so we shall consider this phasor along x-axis. So the phasor for the AC current in this series combination is a reference phasor. We shall consider the angle of the voltage across the capacitor with respect to this phasor. We shall consider the angle of the phasor of the voltage across the capacitor with respect to this phasor. We shall consider the angle of the phasor of the AC voltage across the source with respect to this phasor. So the phasor for the current is known as a reference phasor. We consider the instantaneous equation for the voltage across the resistor. We know that the voltage across the resistor is in phase with the current. So if the phase angle of the current is 0, then the phase angle of the voltage across the resistor will be 0 as well, because these two quantities are always in phase. There is no phase difference between the current in the resistor and the voltage across the resistor. So omega t in this particular equation can be written as omega t plus 0, where 0 is known as the phase angle of this voltage. So the phase angle of this voltage is 0. The phase angle of this voltage is 0. So omega t is written as omega t plus 0. 0 is the phase angle of this AC voltage. So the phase angle of this AC voltage is known. Let us calculate the RMS value of this AC voltage. So we divide the maximum value of this AC voltage by under root 2. So if we divide the RMS, if we divide the maximum value of this AC voltage by under root 2, we get the RMS value of this AC voltage. And if we simplify this equation, then the RMS value of this AC voltage is equal to the RMS value of the AC current multiplied by the resistance of this series combination. So this is how we calculate the RMS value of the AC voltage across the resistor. is the RMS value of this AC voltage is known and the phase angle of this AC voltage is known, we can represent this AC voltage with the help of a phasor quantity. So this is the phasor value of this AC voltage, and the phasor value of this AC voltage is in polar form. The magnitude of this phasor is equal to the RMS value of this voltage, and the angle of this phasor is equal to the phase angle of this phase angle of this voltage. We convert the polar form of representation into a rectangular form of representation. So if we convert the polar form into rectangular form, the imaginary component of this AC voltage will be 0, and this phasor will have the real component only. The real component will be equal to the RMS value of this AC voltage. So this voltage is a real phasor. We know that all the real quantities are taken along x-axis, so the phasor for the voltage across the resistor will be along x-axis because the voltage across the resistor is a real phasor. Now we consider the instantaneous voltage across the capacitor. So we consider the instantaneous voltage across the capacitor. This is the instantaneous voltage across the capacitor, and the instantaneous voltage across the capacitor is equal to Im xc sine of omega t minus 90 degree. We know that the voltage across the capacitor lags behind the current by 90 degree. In other words, the current in a capacitor leads the voltage across the capacitor by 90 degree. In other words, there is a phase difference of 90 degree between the voltage across the capacitor and the current in a capacitor. So the phase angle of this AC voltage is known, and the phase angle of this AC voltage is minus 90 degree. We calculate the RMS value of this AC voltage. So in order to calculate the RMS value of this AC voltage, we divide the maximum value of this AC voltage by under root 2. So here is the RMS value of this AC voltage. The RMS value of this AC voltage is equal to Imxc over under root 2. If we simplify this equation, we get another equation, and the RMS value of the AC voltage across the capacitor can be calculated with the help of this equation. The RMS value of this AC voltage will be equal to the RMS value of the AC current times Xc, where Xc is known as the capacitive reactance of the capacitor. This is the capacitive reactance, and this is the property of a capacitor, due to which it opposes the flow of AC current, is known as capacitive reactance. So as the RMS value of this AC voltage is known and the angle of this AC voltage is known, we can represent the AC voltage across the capacitor with the help of a phasor quantity. So this phasor is in polar form. The magnitude of this phasor is equal to the RMS value of the voltage across the capacitor, and the angle of this phasor is equal to the phase angle of the voltage across the capacitor. So the phase angle of the voltage across the capacitor is minus 90 degree. We convert this polar form of representation into a rectangular form. So if we convert the polar form into rectangular form, the real component will be 0, and the imaginary component will be negative. So the voltage across the capacitor will be equal to minus J I RMS times XC. So the voltage across the capacitor is an imaginary phasor. This imaginary phasor is negative. So if we want to draw this phasor will be along negative y-axis. So the phasor for the voltage across the capacitor will be along negative y-axis. We consider all the imaginary quantities along y-axis. Y-axis is known as the axis of imaginaries. So the phasor for the voltage across the capacitor will be along negative y-axis. We consider this series circuit once again. So let us go back to this series circuit. This is the series combination of the resistor and capacitor, and we apply KVL to this series circuit. According to KVL, the phasor sum of the voltage rises in this loop will be equal to the phasor sum of the voltage drops. So if we focus on this loop, the voltage across the source will be equal to the phasor sum of the voltage across the resistor and the voltage across the capacitor. So if we take the phasor sum of the voltage across the resistor and the voltage across the capacitor, this phasor sum results in the voltage across the source. So Vs in this particular case will be equal to Vr plus Vc. Let us consider this equation in its proper slide. So we apply KVL to this series circuit. According to KVL, the voltage across the source will be equal to the phasor sum of the voltage across the resistor and the voltage across the capacitor. So we apply KVL to the series circuit of resistor and capacitor, and we obtain the first equation where Vs is equal to Vr plus Vc. We consider the phasor diagram of this RC series circuit. So the phasor for the current is along x-axis. This is a reference phasor because we shall consider the angle for the phasor Vr with respect to the current phasor. We shall consider the phasor for Vc with respect to current phasor, and we shall consider the angle of the phasor Vs with respect to current phasor. So anyhow, we draw the current for the phasor along x-axis, and this phasor is known as reference phasor. The phasor for the voltage across the resistor is along x-axis because this is a real phasor as well. The phasor for the voltage across the capacitor is along negative y-axis because this is a negative imaginary phasor. So the phasor for the voltage across the resistor is along x-axis, and the phasor for the voltage across the capacitor is along negative y-axis, and you see the voltage across the capacitor lags behind the current by 90 degree. We consider the phasor sum of the voltage across the resistor and the voltage across the capacitor, and this phasor sum results in the phasor for the source voltage. So the phasor sum of the voltage across the resistor and the voltage across the capacitor results in the source voltage. We add the phasor for the voltage across the resistor and the phasor for the voltage across the capacitor according to head-to-tail rule, and the addition of these two phasors results in the phasor for the source voltage. So this is the phasor diagram of this RC series circuit. This is how we calculate the phasor value of the source voltage. There is another way to calculate the phasor value of the source voltage. Let us consider the instantaneous equation of the source voltage. The source voltage is equal to Img sine of omega t minus theta. So the phase angle of the source voltage is minus theta. Let us calculate the RMS value of the source voltage. In order to calculate the RMS value of the source voltage, we divide the maximum value of the source voltage by under root 2. The division of the maximum value of the source voltage by under root 2 results in the RMS value. If we simplify this equation, the RMS value of the source voltage will be equal to the RMS value of the current times Z, where Z is the impedance of this series combination. So we know the RMS value of this AC voltage and the angle of this AC voltage, so we can find out the phasor value of this AC voltage. The phasor value of this AC voltage is in polar form. The magnitude of this phasor is equal to the phasor value of this AC voltage, and the angle of this phasor is minus theta, which is the phase angle of this AC voltage. And keep it in your mind that the source voltage lags behind the current by theta, where theta will be less than 90 degree. We can calculate theta. Let us focus on the phasor diagram. If we focus on the phasor diagram, there is a right angle triangle in this diagram, and each side of this right angle triangle gives you some voltage. The base of this right angle triangle gives you the voltage across the resistor. The perpendicular of this right angle triangle gives you the voltage across the capacitor, and the hypotenuse of this triangle gives you the voltage across the source. So let us consider this voltage triangle on the next slide. So we consider the voltage triangle of this RC series circuit. The base of this triangle gives you the voltage across the resistor, which is equal to IR. The perpendicular of this triangle gives you the voltage across the capacitor, which is equal to IXC, and the hypotenuse of this right angle triangle gives you the voltage across the source, which is equal to IZ. So if we divide all the three sides of this right angle triangle by the current, we obtain another triangle which is known as the impedance triangle. So this is the impedance triangle of this RC series circuit. The base of this triangle gives you the resistance of this series combination. The perpendicular of this triangle gives you the capacitive reactance of the capacitor, and the hypotenuse of this triangle gives you the impedance of this series combination. And if we focus on this impedance triangle, we conclude that the impedance of this RC series combination is a complex quantity. The real component of this complex quantity is equal to R, and the imaginary component of this complex quantity is Xc. As Xc is along negative y-axis, so this component will be imaginary and negative. So the impedance of this series combination will be equal to R minus jXc. So this is how we calculate the impedance of this series combination. The impedance of this series combination is a complex quantity. The real component of this complex quantity is R, and the imaginary component of this complex quantity is Xc. So if we want to calculate the magnitude of this complex quantity, the magnitude of this complex quantity will be equal to under root square of the real component plus square of the imaginary component. So the real component of this complex quantity is R, and the imaginary component of this complex quantity is xc. So this equation gives you the magnitude of the impedance of this series combination. If you want to calculate a theta will be equal to tangent inverse xc by r. So we can calculate theta with the help of this particular equation. We have tangent inverse xc by r. So we can calculate the magnitude of this impedance, and we can calculate the angle of this impedance with the help of this particular equation. If we focus on this impedance triangle, so you see cos theta in this right angle triangle, I am talking about the impedance triangle. So cos theta in the impedance triangle will be equal to the base of this triangle divided by the hypotenuse of this triangle. So cos theta will be equal to r by z. Cos theta is known as the power factor of this series circuit. So if you guys want to calculate the power factor of this series circuit, the power factor of this series circuit will be equal to cos theta, and we can calculate cos theta with the help of the right hand side of this equation, which is r by z. So the power factor of this series circuit is equal to cos theta. So this is the power factor of this series circuit. The power factor of this series circuit will be equal to cos theta, where cos theta is equal to r by z. The power supplied by the source can be calculated with the help of this equation. We have the square of the RMS value of the AC current times resistance of this series circuit. So we can calculate the power supplied by the AC voltage source with the help of this particular equation. We know that the RMS value of the AC current in this series combination will be equal to the RMS value of the source voltage divided by the magnitude of the impedance of this series combination. If we put the value of this AC current in one of the two i's, you see we have I squared, so there are two i's in this equation. If we put the values, the value of the AC current in one of the two i's of this equation, we get this particular equation. So the power supplied by the source will be equal to V S RMS times IS RMS times the power factor of this series circuit. So we can calculate the power supplied by the voltage source with the help of this particular equation. So if the RMS value of the applied voltage is known, if the RMS value of the AC current in this series combination is known, and if the power factor of this series circuit is known, we can calculate the power supplied by the source to the entire circuit. According to the law of conservation of energy, the power supplied by the source will be equal to the power consumed by the entire circuit. So we can calculate the power supplied by the source with the help of this equation. Thank you so much.